Vectors are geometric objects that have both magnitude and direction. Vectors have many theoretical applications, but importantly they also have many real-world applications and can be used to represent the motion of bodies through space. There is a whole field of geometry dedicated to mathematical operations in vector space called vector algebra, which can exist in two-dimensional, three-dimensional, or higher dimensional space. But the beautiful thing about vectors is how their operations in classical Euclidean space can be visually represented. Take, for example, the two-dimensional vector A, which has an x and a y component. Now let's add to it another vector B, which has its own x and y components. If we were to add these two vectors together mathematically, then we will simply sum the x and y components of each vector to find the x and y components of the resultant vector, C. But there is another way to sum vectors, and this is where theory meets reality. Let's say that we have the same vector A. It has magnitude and direction. We also have our old vector B, which has its own magnitude and direction. Now, if we were to sum these two vectors, we would join them tip to tail, and the resultant vector C reaches from the tail of A right through to the tip of B. And if you measure the x and y components of this resultant vector C, you will find that it is equal to the sum of the x and y components of vectors A and B. Now let's apply this to a real-world scenario. I want you to think of balls on a pool table. If the two balls were traveling at a constant velocity, which is a constant linear speed that has both magnitude and direction, so this can be represented with a vector, and then suddenly two balls collided with the bumper at the edge of the table, what do we observe? Well, two balls cannot keep traveling at a constant velocity. The bumper is in the way, and the bumper has blocked its constant linear velocity. We have all played the game pool before, and we all know that the ball reflects off the bumper at the same angle at which it collided. To get a better understanding of what we have just observed, let's take a look at the velocity vectors. We will set up our Cartesian axis so that the bumper is parallel to the x-axis. In problems like these, I will encourage you to set up your axes so that the bumper or the wall or whatever is parallel to one of the axes, as it creates very clean and simple calculations. Let's break the angular velocity vector of the ball up into its x and y component vectors. If the ball were to travel with only the x component of its velocity, then there is no collision, and the ball will continue to travel at a constant velocity without interruption. Now, if we were to observe only the y component of the ball's velocity, then what we see is a normal collision, or a right-angled collision. What kind of reaction happens here? Well, much like a basketball bouncing on the floor, Mr. Two Ball is going to rebound or ricochet off the bumper and return. Now, to completely understand what's happened here, we must consider a concept in physics called the conservation of momentum, which states that the total momentum of a system after collision must equal the total momentum of a system before the collision. And if this system were perfectly and truly closed, so that is to say no energy is lost through heat, sound, etc., then the ball will reflect at exactly the same magnitude but different direction to the initial vector. The two ball has mass and velocity before the collision. After the collision, the mass of the ball remains constant, of course, and as this is the only object involved in our closed system, then the magnitude of the velocity of the ball must also remain constant after the collision, although it will be traveling in a different direction. Now, let's put all of this together. Let's take the initial vector, which represents the ball approaching the wall at a constant velocity. Let us break that vector up into its component vectors. After 2 units of time have elapsed, let us return the component vectors back to their true trajectory vectors and observe the results. We see 4 very interesting things here. Firstly, the outgoing reflecting vector has the same magnitude as the original incoming vector. The angle at which the vector approaches the wall is equal to the angle at which the vector ricochets off the wall. The sum of these two vectors is simply the sum of the y components of the vectors, and this comes as no surprise as the equal and opposite x component vectors will cancel each other out, and lastly, that the sum of these vectors is parallel to the wall. Now, if we were to do exactly this same problem, however, with a wall that was not parallel to one of our Cartesian axes, then we will still approach the problem the same way. Sure, there will be a little bit more work involved, but ultimately we will still arrive at the same results and conclusions, particularly that the angle of reflection is equal to the angle of approach. So for these particular vector collision problems, at the point of impact we could draw a new axis perpendicular to the wall. We shall call this the axis of reflection and recognize that this axis acts as a mirror of sorts, that after collision, the second vector shall have the same magnitude and the same angle about the wall as the original vector. What's curious is that if we were to sum these two vectors, the resulting vector will still run parallel to the wall. Whoever would have thought that a simple game of pool could involve so much mathematics?